Hello everybody, my name is Peter Klapper from the School of Biosciences at the University of Kent, and in this video clip I would like to talk about the specificity, sensitivity and predictive values of a clinical test. Now here is the scenario. We have an infectious disease which affects 2% of the population. A new test has been developed that detects the disease in 97% of the cases. It also detects healthy individuals in 95% of the cases. And we want to know what is the specificity, the sensitivity, and the predictive value of this test. Now, how can we address this? First of all, we can come up with what is called a decision tree. And we say, okay, we have our disease, and we either have this disease, so plus, and since 2% of the population are affected, 2% have this disease, or they don't have this disease, so that would be the remaining 98% of the population. Now we can say for these 2% who have the disease, the test is either positive or the test is negative. And we know that the test is positive in 97% of the cases. And in 3% of the cases, obviously, the test is negative, although people have the disease. Now we can do that also in the case of when people are not affected. So we can say the test is positive in 5% of the cases, and it is negative, test negative, in 95% of the cases. So we know that it detects healthy individuals in 95% of the cases. And now we can, in a way, we can convert this into numbers, and we can say what is 97% of these 2%. And this would give us, when we get the calculator out, so that is 0.97 times 0.02. And this gives us 0.0194. Likewise, here we can say 3% of 2%. These are the individuals that have the disease but test negative. And this would give us 0.03 times 0.02. This gives us 0.0006. Here we have 5% of 98%, like that, and this would give us 0.049, and in this case here we have 95% of 98%. So that gives us 0.95 times 0.98, and that would give us 0.931. Now, of course, it is a little bit tricky in a way to work with all these percentage numbers. And what we can do instead is we can translate these numbers into full numbers. So we can say we just take a population of, say, 10,000 people and multiply all these numbers that we have here, multiply them simply by 10,000. So 0.09194 times 10,000, that gives us 194 people. This number times 10,000 gives us 6 people. This gives us 490 people. And this would give us 9,310 people. So we have a nice list, and we can convert these numbers now into a contingency table. So for the positive test and positive disease, we have 194. Positive disease, negative test, we've got 6. Negative disease, but the test is positive, 490. And negative disease, negative test is 9,310. Now let's put these data in. So we have let me just quickly change the color. For the positive test and positive disease, we said we have 194. And if we don't have this disease but test positive, this is 490. And we can also do the total here. We just add these two together, 194 plus 490. This gives us a total of 684 individuals. 684 individuals test positive. Now, disease, yes, so people who have the disease but test negative, we said this is 6. And we can calculate again the total here, 194 add 6 gives 200. We said 490 people test positive but don't have the disease, and 9,310 people test negative and don't have the disease. So we have a total, I don't know why this is doing this, 9,800 don't have the disease. And the total of this is 10,000. That was our population. We could have chosen any other number, but this is simply what was probably easiest in this case to choose, so that we get whole numbers. Now, the first thing that we can calculate, or that we almost know already, is a term that is called prevalence of the disease. And the prevalence tells us how many people in the population are affected by the disease. So that's quite easy, because we know that 200 people have the disease. So 200 out of a population of 10,000. And therefore our prevalence equals 200 divided by 10,000. And this gives us 2%. So that is our prevalence. Now let's have a look at the other data, and I just realized I forgot to put in the data, the total for this one, so that will be 9,316 people here. Right, now let's have a look at the other test parameters. So here I've typed up the numbers, hopefully correctly. And let's talk about what is called the term of sensitivity. Sensitivity, this is defined as the number of positive tests in the disease, so number of people who are positive for the disease and positive for the test, divided by the total number of people who are positive for the disease. And in our case, the sensitivity would be A divided by A plus C. So I labeled these different cells with A, B, C, and D. So the sensitivity in this case is A divided by the total number of people with disease. So in this case, it would be who test positive 194 divided by 200, and this gives us 97%. So sensitivity tells us how many of the people who are affected actually test positive. So the sensitivity in this case is 97%. Let's have a look at the specificity. Specificity of the test. The specificity is how many people who are not affected test negative. So how many people not affected test negative. And in this case, we can say it is D divided by B plus D. So this would be 9,310 people who test negative and don't have the disease, divided by 9,800. And if we do that, this gives us a specificity of 95%. Now it's quite interesting because in a way we already knew this. When we go back to our scenario, we knew the prevalence, that is how many people are affected by the disease, and we also knew the specificity and the sensitivity. We knew the sensitivity here. That's the 97%. It detects the disease in 97% of the infected cases. So that is our sensitivity, and that is our specificity here. So we already had these data in a way given to a certain point. Now, another very interesting thing is what is called the negative predictive value of the test, or it's also abbreviated as NPV. And this is really how likely is it if your test is negative, how likely is it that you are truly negative? Truly negative, or in other words, not affected by the disease. And we can calculate that quite easily. We can say negative, you test negative, so it is D divided by the total of negative tests, so divided by C plus D. So we just put in the numbers, and this is 9,310 who are not affected by the disease and who test negative, divided by everybody who tests negative, and that is 9,316. And if we calculate that, then this is 99.94%. So if you test negative, if the test is negative, you can be sure, you can be 99.94% sure that you don't have the disease. Disease negative, which is quite nice. So you test negative and you can be fairly certain that you don't have the disease. Now, what is the predictive value? The positive predictive value. Positive predictive value. This tells you that if you test positive, if the test is positive, how likely is it that you are also positive for the disease? And this has a major effect on how people feel about these tests. And in this case, we calculate the number of people who are positive for the disease and who test positive, so that would be our A, that is this number here, A divided by all the people who test positive, so that would be A plus B. And in terms of numbers, it would be 194 divided by 684, which gives us a positive predictive value, which is also abbreviated as PPV, of 28.36%. Or in other words, you test positive test, and you have a 28.36% chance that you actually are with the disease, so that you are positive for the disease. Or, in other words, you can also say that if you test positive, there is an 71.64% chance that you don't have the disease, that you are actually negative for the disease. So when you go to the doctor and the doctor says, oh, you tested positive for the disease, it does not necessarily mean that you have the disease. In this case, there's only a 28%, less than 1 in 3 chance that you have the disease actually. So there is a very good chance that although you are positive with the test, you don't have the disease. And that is very important to realize the next time you have a positive test, that you ask about the positive predictive value for the test, because that gives you a good understanding whether you have the disease or not. In this case, where the predictive value is something like that, 28.36, it would be a very good idea if other tests are performed that give you another set of data, and where you then can confirm, yes, you have the disease, or no, you don't have the disease. So hopefully this makes sense to you. These 4 or 5 values: specificity, sensitivity, negative predictive value, and positive predictive value, and prevalence, obviously, they are very important parameters in clinical testing. Thank you very much for watching.